we would like to thank and acknowledge our sponsors, DC3 Dreams and Boyce Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay, on to the good stuff. Our speaker for today is Francois Cochard, who is an expert amateur spectroscopist that you will probably recognize. Francois has been deeply involved in spectroscopic education for years and has taught at dozens of educational events, including several past AAVSO broadcasts. His list of accomplishments is long. He's the organizer of the annual OHP Spectro Star Party in France, the author of the book Successfully Starting in Astronomical Spectroscopy, A Practical Guide, and the co-founder of Shelyak Instruments, where he produces many of the standard spectrographs which are in use by amateurs today. In short, Francois is an expert, not only when it comes to spectroscopy itself, but also when it comes to teaching people about spectroscopy, which is why we are all very lucky to have the chance to learn from him today. Ladies and gentlemen, I give you Francois Cochard.
Hello to everybody. Thank you so much, Lauren. So thank you for your impressive presentation. So now I do have the pressure on me. Thank you so much. So hello to everybody. I will share my screen to show the slides. I will work with. I hope that you can see my screen now.
Looks great.
Well, perfect, thank you. And this is really a great pleasure to talk to you. When I see the list of the names, I know a few of you, but not a lot of them, in fact. So I think most of you are really beginners, which is a great news, because it means that more and more people are jumping into spectroscopy, and then the idea for me is really to talk about you as beginners tonight. Well, tonight in France, today for you, so I will not talk about the spectroscopy itself, but I consider that you are interested to do spectroscopy by yourself, and you don't know exactly how to start with, or you have some ideas, but you would like to have some advice, and then I will give you this advice to start. Okay, so what I will talk about, if it's okay for you, I will have a quick introduction. I will give you a few tips about the general approach when you are doing spectroscopy, about the instruments, about the observation, and of course about data processing. Okay. And then we'll see very quickly what makes a good observation, and this is very basic, in fact. And I will also give you a few words about the Solex project, which is a new instrument proposed by Christian Bruil. And this is something which is very amazing, I think, and which is a wonderful instrument to start with in spectroscopy. And of course, we'll finish by the discussion, and you can. It will be really a pleasure for me to reply to all your questions. Well, I hope it's okay for you. So I start with that. And the first thing that I want to tell you is that we can really start in spectroscopy with a small instrument. So there is no need for a big telescope, a big setup, dome, and so on. So you can start with a simple instruments, and this is something very important for me, and in fact very amazing. So the quality of your data doesn't depend on the quality on the size of your instrument. Okay, the quality of your data will depend on the way you are managing your observation, but you can do that with a small instrument. Of course, you will not have the same result with a small and a big instrument. There is a real interest to have a big telescope to go for fainter targets, but the quality, you can have a very high quality observation with a small instrument. Okay, so also something important for me is this talk is valid for high resolution as well as for low resolution. You know that when we are doing spectroscopy, we can have low or high resolution observations. So when we are doing low resolution, we have a wide bandwidth covered by the spectrum. We can observe the whole visible spectrum in a single shot. And when we are doing high resolution spectroscopy, we just focus and we zoom, in fact, in a small part of the spectrum, and then we see much more details, for example, in the line profile of a specific line profile. But both are quite different. But all of what I will tell you today is really valid for both of them. Okay. Something else which is a key for me today, this is to tell you, this is very important for me. When we are doing spectroscopy, we are doing simple things. Okay, spectroscopy is really simple. There is one thing which is a little bit complex, which is that we have to put under control several points, or maybe a lot of points. Okay, and we will cover most of them, but each point is very easy to manage. Okay, so we are not doing I mean, when we are doing observations in spectroscopy, we are not doing astrophysics. That can be quite complex. We're not doing quantum mechanics, which is for sure quite complex. But taking spectra is something, in fact, very basic. But we have to put a lot of things under control. And of course, if in spectroscopy observation depends on, say, 10 different parameters, if each parameters is not really under control, so for sure at the end the observation will fail. Okay, so we must be very methodic and put every point under control, and the idea is really to put them under control step by step, one by one. Okay, and it's much better to not try to control them all at the same time. Okay. Another important point is when we are doing spectroscopy, the goal of the observation is to get a clean and calibrated data. Okay, the idea is to have, I would say, I don't want to make you afraid, but we have to have a scientific result. Okay, again, it can be a simple scientific result, so don't be afraid, please. But the result is something that I have in the screen here. So I hope that you can see my mouse on the screen. And these are, for instance, two different spectra, one from Vega and one for YCVN, which is a carbon star, and taken with the same instruments in same conditions. And of course, we can see the difference between the different observations. The idea is really, so this is the result of an observation. So you have a spectrum profile, which is corrected from all the instrumental effects, okay, and which is properly calibrated in flux and in wavelengths. Okay, so this is the result. So keep in mind that doing spectroscopy is not only taking images on the telescope, but it's also to go up to the final result, which is this calibrated profile. Okay. When I'm preparing this talk, this presentation, I do have in mind this kind of instruments. Well, this is my old telescope, my previous telescope. I have a new one now, but it's not really bigger than that. So I have a better mount, but the idea is the same. And this is on the picture. So it was taken at the OHP, so at the Observatoire de Haute Provence a few years ago. And this is really, this is a C8, on an old mount, and you can see here there is then an LP. You can see the LP, the calibration module. You can see the acquisition camera and the guiding camera. And I do have two computers. Well, I did have at this moment two computers, which is better because one is controlling the telescope and the other one is controlling the acquisition. And just a small detail about that, it's more comfortable to have two different computers because you have more screen surface and more information at the same time. But really, there is absolutely no need to have several computers regarding the computing power of the computer. All the software that we are using during the acquisition and the data reduction can be done with a single computer with no problem. But this is just the advantage of having a different way to control the different elements, and we have a better control. Okay, so again, I'm not talking about big instruments. Even, of course, if you have a big instrument, if you are lucky enough to have a big instrument, all the recommendations will be also absolutely valid, and the idea will be exactly the same. But generally speaking, it will be easier to start with a small instrument. Now, I start with some general statements about spectroscopy. I told you that nothing is complex when doing spectroscopy, but we have to put several points under control. Knowing that, I think it's important to start with these kind of recommendations. Please go back to basics always. This is a sentence from Steve Shore that I love. He told us a few years ago, well, always know why you are doing what you are doing. I like this because, well, this is obvious, of course, when you are doing an observation. It's of course we are going back to basics. The problem is that when you are in the middle of the night, when it is 2 or 3 o'clock in the morning, you probably know that we don't think the same way, and we are maybe less clever than during the day. And it's very important to say, okay, so if something is happening during my observation, please keep in mind that things are simple, and the astronomy is something very rational. Okay, and let's try to keep things simple and take some time to understand what is happening. Okay, this is the same idea. Never let the computer make the decision for you. So you are the boss. This is not the computer or the software or the acquisition software or the data reduction software which is the boss. You are the boss, and then the computer is here to make what you have decided to do. This is basic. This is even stupid. I'm sorry for that, but really this is something important. I know that in the middle of the night we may have some strange behavior, and this is a pity. Also, something which is important for me, I love the continuous improvement approach. So it means that the idea is do your best to have a first spectrum, even if it is a poor observation, but try to have a first spectrum and then improve it step by step, and look at your data, look at your result and say, hey, what can I improve to have a better observation for next time? And this is very important to have this approach, a small step every day. So in this mindset, again, do your best to have a first observation as soon as possible, as fast as possible, even if it is not good. But do that, and then look at your data, you get the result and say, okay, so now I've done this first observation. what can I improve? Redo it several times and then compare the results. Are they always the same or are they different? What did you change to change the result? Is it an improvement or is it worse than before? Okay, so this is a general approach which is very important when doing spectroscopy. Of course, it can be applied for many other areas, general astronomy or even elsewhere, of course. You have to choose your preferred softwares. We have to use different software. Generally speaking, you need one software to control your mount, and control your mount means going to the target, but also guiding or auto-guiding the mount, and to make sure that you put the star in the slit of the spectroscope. You need a you need a software to do the spectra acquisition. You need another piece of software to do the data reduction. And finally, you usually need a sky map to know where you are looking at and to control that you are looking at the right star. Well, by the way, I can promise that even the most experienced people I know have already made a mistake to shoot to observe the wrong star. So well, I will not give you some names, but I can tell you that everybody has made a mistake at least one day to say, okay, so I want to point at this star, and finally this is just the star beside. Okay, so don't be afraid. This is something quite normal, but also put this under control. So make sure that you have some way, some tools to make sure that you are observing the right star. Something else which is very important when doing spectroscopy is do your best to observe regularly. This is important. I know that we have people coming at the OHP every year, and some of them come every year saying, well, I didn't have the time to observe during the year. And if you do that only once a year, I can promise that it will be very difficult to do some progress, because from one day to one year to the other, to the next one, you will forget all you have learned. So it's important to do regular observation. The good news, which is very important, is that you can do spectroscopy even in city center, even at home. Personally, well, now I do have a home with a garden, so I'm in good conditions. But for a long time, I was in a flat in city center, and my instrument, my telescope and spectroscope was on the balcony, and I just saw a small part of the sky, but it was enough to do some tunings and how to play with the software, make sure that the connection with the camera is okay, how to select the parameters for the auto guiding and so on. All these things can be done even with a poor sky. So it's something which is very important. So when doing spectroscopy, you don't necessarily need to have a wonderful sky like it is usually when you are doing great pictures. Okay, so it's an important point. Observe regularly and do some capitalization of your experience, and again, improve step by step by observing regularly. And a very good way to make great progress is really to share your results, and why not to join collaborative programs. I know that when you are a beginner, you often think that, okay, so you are a beginner, so you are not an experienced guy, so you cannot show your results, and you will keep them for you, and you don't dare to show what you have done. I can promise that this is showing your result, even if they are bad, even if they are poor, is the best way to have advices from the community And you know that this astronomy community is a great community, so I'm sure that you'll have a lot of advices. And for me, this is the best way. If you are alone in your backyard and if you never want to share what you have done, it will take much more time to do some progress. So my recommendation is really share your result, show what you have done. And by the way, if you participate to a collaborative program, then you will have a community of experts that will help you to improve your observation. This is also something that I like to tell to people starting in spectroscopy. The experience I have is when you are doing photography, when you are taking great pictures of nebulae, galaxies, and so on. This is a never-ending story. So you always have to improve. You can always improve something. You can expose for a longer time. You can have better filters and data processing and so on. So really, it's a never-ending story. When you are doing spectroscopy, it's a little bit different. You need to have some time to learn how to take a spectrum and process data and produce a clean and calibrated data. But once you have done that, once you have understood how it works, once you have put under control all the parameters I was talking about, then at this moment, you are ready to take spectra of anything. And at this moment, you are done with the technical side of the story, and then you can switch to the science. Okay, so this is really something important. So of course, it will depend on your instruments. And if you change your instrument or if you change something in your instrument, you'll have to go back to technical stuff to put that under control. But really, this is something very important. When people know how to take a spectrum, then you know how to repeat it every day, every night, and it's really a pleasure to switch to science. Okay. Well, by the way, it's really a pleasure to have all of you. I see that there are 77 people online. It's a little bit frustrating to not see you and to not have your question in direct and questions. So that's life. Anyway, I know that we will have some time for the questions at the end, but I would like to make sure that it is okay for you and tell me if you have any questions. I will look at the questions and question and answer. Okay, so now let's switch to some tips about the instruments. Okay, the instrument itself. Something very important. Maybe if you have to keep in memory one advice tonight, it is this one: make your first spectra on a bench, on a table. So don't put the spectroscope when you receive it on the telescope immediately. Take some time to use your spectroscope on a bench, and once it is under control and once the telescope is under control, then you can put the spectra onto the telescope. But these are two different instruments, and both of them must be controlled, must be mastered. And this is really, I repeat it very often. I know that when you receive your spectroscope, the temptation is huge to put it on the telescope and try to catch a spectrum, star spectrum, as quickly as possible. I can promise this is a mistake, okay? And even if you can do it, even if you are successful to take a spectrum of a star the first night, I'm sure that it will be because you are lucky and you are not able to do it to do it again the next time. So really consider that these are two different instruments that we use together to take star spectra. But when you are using your instrument on a bench, on your table, at home, in good condition, during daylight, you can use the light, you can use any light source that you want. So the sun light, of course, but the light you have in your room, you have calibration lamps, you can use flames, you can use any lamps that you have in hand. And in fact, all the light that goes into the spectroscope through the slit can be analyzed. So you can really start by taking spectra of any light you have at home. Okay, so this is important. And then you also have to control your telescope without the spectroscope. So I know that for most of you already know how to control the telescope because you're observers, because you're AAVSO members. Just keep in mind that there is a specificity in spectroscopy, is that we are not looking at a region of the sky, but we are looking precisely at one star, okay, and a given star. And there is something which is not easy at the beginning. If I ask you, for instance, well, recently at the beginning of August, we had a nova in the sky, which is RS of focus. And the first time, if I ask you just to point at this star, it can be quite difficult for beginners because, you know, okay, where is this star? How can I find it? Okay, so we will I'll come back on that later on, but this is something that you have to keep in mind when you are doing spectroscopy. You must put a given star at a specific position in your image. And when I say specific, I mean at few pixels of precision, because the slit image in your guiding image is few pixels only. Okay, so it means that you must be able to put exactly one star at a given pixel. Okay, so it can be impressive when I present that this way, but in fact it's quite easy to do when you have the right setup and using the guiding camera and so on. To when the instrument is properly tuned, this is something that we can really. This is not difficult to do, but this is something I'm just mentioning that because this is something which is different between general observations and well, I mean general observation when you are doing imaging or astrometry or the measuring the photometry of variable stars, and you don't need to have the same precision to point your telescope. Okay. Well, when both the spectroscope and the telescope are under control, then you can you can put the spectro on the telescope. Okay, in this case, you have to make sure that it is strongly attached, because if there is any gap, any free movement, you'll have big problems to put a point at stars, because depending on the position of the telescope, you'll have the spectrum will be moving, and then it will be very difficult to put the star in the slit. Okay, and also you have to take care of the balancing of the mount and the cable management. When we are doing spectroscopy, we have usually 2 or even more cameras. You have the cables for the mount itself. You have the cable for the different power supplies and so on. So you may have quite a high number of cables, and make sure that you have a proper path for the cables to make sure that when moving the telescope, there is no risk to unplug any cable, okay, or unplug cable, or pull on the mount and make the guiding failing. Okay. Of course, you must have to have a good alignment, or the good mount alignment. So you must align your mount to the polar star, or the rotational axis of the Earth. And so these alignments must be good enough. It is not necessarily perfect at the beginning. Okay, so remember at the beginning I told you that you have to get a first spectrum and then improve it step by step. So this is typically a step that can be improved over the time. There is no need to have a perfect mount alignment. I've seen several people saying, wow, this part of the installation of the instrument is quite complex, and then I will spend a lot of time to do that. And in fact, maybe it's not necessary, especially because if you are observing bright targets, which is a recommendation for the first observations, of course, then the exposure time will be very short. So if the exposure time is short, you don't really care if the guiding is not perfect. Okay, so you'll have to improve the mount alignment, you have to improve the guiding and so on when you go to fainter stars. But at the beginning, this is not a very high expectation. Okay, small advice also, prefer a remote operation. When I mean remote operation, I mean usually when you're starting spectroscopy, you have the telescope and you have a table just beside the telescope, and you work from the table. And it is better if you don't have to go to the telescope, for instance, to switch on the calibration of the flat light, or maybe to point at a star. It's better if you have a way, for instance, with a go-to mount, to point automatically at the star, not using to put the eye in your eyepiece or in your sky finder. Or as soon as you touch, you put the hand on the telescope, there is a risk to move something, to unplug a cable or something like that. So it's always more comfortable to work remotely. So of course, it really depends on the instrument you have. For some of you, it's very easy and it's obvious. For some other, you have an instrument that you really use manually. So if it is the case, don't change it, keep this instrument and do it manually, but just have that in mind. It's always better to not touch at the instruments during the operation. Okay, so I like also the idea, if it works, don't fix it. So it means that you have to tune your instruments, but once it is tuned, please don't change anything else. Keep the instrument as it is. And also, I recommend to take some pictures of your configuration to look at the orientation of the camera versus the spectrometer, the orientation of the spectroscope versus the telescope, and so on, to make sure that next time you will recover exactly the same configuration. And then when you will work on your computer to take the images, you'll have exactly the same behavior. Okay, if you rotate the camera, for instance, on the instruments, maybe today the spectrum will be horizontal in the image, and then tomorrow, if you rotate the camera, the spectrum will become vertical, which is not a good idea, in fact. Okay, so when the configuration works, please don't change anything else and keep it as it is. And another point regarding the instrument. Again, this is an important point. Focus the guiding camera on the slit first. Okay, so I do have an image, I think. Yes, I do. So this is symbolic representation. So you have the light coming from the telescope here, and the job of the telescope is to collect all the light from the star and to focus it in the focal plane. Okay, and in the focal plane we have the slit, which is here, and we have usually the slit is put on a mirror, and this mirror allow to send the field telescope field image towards the guiding camera, where the light that goes through the slit goes to the spectroscope. Okay, what I'm saying here, I'm talking about the focusing of the camera, guiding camera here and the telescope. Okay, so it is absolutely important to focus the guiding camera first, and generally it is during the light, and to make sure that you can see the slit perfectly sharp in your guiding image. Okay, why do I say that? Well, the spectroscope is quite independent, so you have to focus the spectroscope on its own, and to do that, we usually use the calibration lamp. So it depends on the instrument, but we use the calibration lamp and make sure that the calibration lines, emission lines, are as sharp as possible. Okay, so this is for the spectrum, but now here I'm talking about the guiding camera and the telescope. Why I'm saying that? Because you may have this situation. I've seen that many times. A lot of users are doing this mistake. This is a very basic mistake. If you are doing that, so in fact, if you put the camera, the guiding camera, and you don't really take care about the focusing of the guiding camera. And then you wait for the night, and during the night, you change the focus of the telescope. And then in this case, you can have the telescope, which is perfectly focused on the guiding camera, and then you can see the stars that are sharp and perfectly sharp in the guiding camera. The problem is that if you do that, you are totally unfocused on the slit, and then you cannot even see the slit, or maybe you can see it, but it is quite fuzzy. Okay, and you have to understand that in this case, the telescope is focusing its image so this is the telescope focal plane, and this is the slit enter. So if you look at that, if you look at the image, the size of the image of the star at this position in the slit, it is huge. Okay, and it is totally unfocused. So you feel that the focusing is correct in the guide, because you can see a sharp star in the guiding camera, but you cannot see the slit. Okay, so this is why it is so important to have the guiding camera focused before during daylight, and make sure that you can see the slit of the spectrum perfectly sharp. And then during the night, you will have to focus the telescope to make sure that the star is focused in the slit. But at this time, during the night, you never change the guiding camera focus to make sure that it is properly focused on the slit. Okay. So I think that's it for most of the instrument itself. We could spend hours, of course, on this subject, but I'm going fast to these different topics. Now I will switch to the observation itself. Okay, so here are some recommendations. Well, I didn't say that at the beginning of my presentation, but all what I'm telling you tonight is, for me, it is really based on, well, first on my own experience. So I can tell you that I've made almost most of the mistakes that I'm describing here. And you know, Lauren, you told at the beginning that I'm an expert in spectroscopy. So it's quite impressive, but my definition of an expert is this is somebody who has already made all the possible mistakes. So maybe in this case, I can tell you that I've made most of the mistakes I'm talking about. So it is based on my experience, but it is also based on all the beginners I've seen and all people I've seen, especially during the sessions at the OHP, at the Observatoire de Haute Provence, that we organize every year. And we have seen a lot of people. We have helped a lot of people, and so what I'm telling tonight is really based on what I've seen there. And well, I guess probably you will do some of these mistakes, but now you will be aware, and I hope it will help. Anyway, I come back to my presentation. Regarding the observation itself, so you have put the instrument under control, so you masterize you master, I don't know, the spectroscope and the telescope, and you have assembled the spectroscope onto the telescope, and everything is ready for a real observation on the sky. So first, again, this is something obvious, but I've seen many times this mistake. Do the installation during daylight. Okay, so the night is only made for the observations, but don't wait for the night to install your setup. And this is a basic recommendation, but it is much easier to doing during daylight. And well, for instance, if you have to I know that if you are doing some high resolution observations and you want to observe the H alpha line, if you want to know exactly where is the H alpha line during the night, it will be very difficult. Where if you do that during the day we have the sunlight, and you just have to look at the sky, and you have immediately the H alpha line, and it's very easy to find it. So this is an example, but to install everything, do that during daylight. Of course, when you are starting for real observations, when I mean real, so I mean a different observation, so the star observation and star other than the sun observations. So after you are finished to do your first observations on your bench or on your table, you can really switch to stars. And then the first recommendation is shoot for bright stars, and it is much easier. The exposure time will be very short. If you take for any instrument, any resolution, and any telescope, I would say, if you observe a Vega or a bright star like that, magnitude 0, 1, 2, the observation, your acquisition will take I would say, well, 1 second, less than 1 second for Vega. And then it is very easy to do. And even if the conditions are not optimal, again, I tell you again what I told at the beginning. So you have to have a first spectrum and then improve it step by step. So even if the tuning of the instrument is not good at the beginning, and if you look at Vega, for instance, well, if your acquisition takes 5 or 10 seconds instead of 1, we don't care. So it's really not a big deal. Okay, so start with bright targets. It's always the best. And then when you start understanding how it works and have great observation, then you can go fainter and fainter and up to the limit of your instrument, of course. So at the beginning, the observations will, the exposure time will be only few seconds. And then when you go to fainter objects, it will take few minutes or even few hours. And of course, if you are shooting for very faint stars that require a few hours, then you'll have to put under control everything, the focusing, the auto-guiding parameters, and so on. Okay. The other recommendation for your first observation is to not use the auto-guiding. Prefer to guide manually. And again, if it's just 1 or 2 second observations, it's quite easy. You just make sure that the star is in the slit of your spectroscope and just run the acquisition, and that's it. Okay. And this is only when you go to fainter targets that you have to set up the auto-guiding, and set up the auto-guiding is one of the steps that you have to put under control, but this is not necessary at the beginning. Okay. Another recommendation to have a good observation is please prepare your observation. If you just install your instruments in the field or in your backyard and say when the night arrives, you say, okay, what do I observe tonight? I don't know exactly. I'm quite sure that the result will not be enough and will not be satisfying. So before that, prepare your observation, select the stars that you want to observe, make sure that the stars are visible where you are during the night, and so on. So if you do this preparation, you'll be much more efficient. Okay. And by the way, if you want to have any coordinate of any star, use the SIMBAD tool from the CDS, so from which is the Center for Documentation of Strasbourg, I think, which is a worldwide database for all the coordinates of any star. It is really a key instrument for us. I told you that if, for instance, I give you the name of RSOF, which is a nova that exploded at the beginning of August, then the first time it's not easy to find. And using this tool, you will find the exact coordinate. And by the way, it comes back to what I said before. So you have to be able to put, to give the detailed coordinates of any star to your mount to make sure that you can point at this target. Of course, if you are playing with bright stars like Vega and Arcturus and things like that, So your mount will know it, and I'm sure that you can find the name of the star in your mount pad, and it's easy to do. But now, if you are looking for fainter targets, I'm not sure. I'm sure that it will not be in the database of your mount, and you have to give the exact coordinates to the system. Okay, and so this is the way to get these coordinates, and try to point a star by giving the coordinates to your mount, and not only the name if it is a common name. Okay, the last point regarding the observations is to look at make sure that you have all your the files you need. So you have to have a spectrum from the target, but you also have to have dark image, BRS image, flat spectra, calibration of spectra, and all of that is required to have the full observation and your full data properly processed. It's a pity if you during the night you just it happens very often also. You take the targets, you take the darks and so on, and the day after you say, okay, so I will process my data. I'm very proud of what I've done last night, and I take my file and say, oop, I forgot to take my flat images, and then in fact I cannot process properly my images. So it's a pity. So also be prepared for that and make sure that you don't forget anything during the acquisition. This is another reason to prepare your observation, in fact. Okay. Regarding data processing, maybe I'm going fast because I'm a little bit late. Regarding data processing, so again, it's important to consider that doing spectroscopy is not only taking images, but it is also process data, because the raw images are not usable. And then we have, after the acquisition, we have to have this task to process the data. Well, today, if you are using some well done software like ISIS or Demetra, for instance, it can really be done in few clicks. And when you're experienced, you can really do the data processing just after your observation. And I can tell you that when we started to develop the Demetra software, for instance, one of the goals was to say, okay, when I finish my observation and when I go to bed, I want to have already processed my data. Okay, because I know it's very dangerous to say, okay, I take the data tonight, and tomorrow or the day after or next week or next month or next year or never, I will process the data. Okay, so it can be very simply, but make sure that you have all you need to process this data in an efficient manner. Keep in mind that an observation is a consistent set of images. Well, by the way, this is something which is very important in Demetra, because we talk about observations and not only about images. But to take a good spectrum at the end, you need to have the target spectra, the flat spectra, the calibration spectra, and so on. And the observation is this consistent set of images. Okay. The next point, for me, very important also, please keep that in memory. Also, this is a very key element. The idea is not to take images and then after that process your images. It should be the reverse. Define your data reduction process, and then during the acquisition, build do the correct images that will fit the data reduction process. This is the key to have a very precise, very efficient way to proceed. Okay, so consider that the data reduction process is the core of the observation, and the telescope is just a simple device to take the data that will fit the data reduction process. Okay, it can be a little bit strange, but I promise that if you do that, you will have a very efficient and easy way to process data, and you'll be very reproducible. So from one day to the other, you'll have always the same process, and you'll have always the same quality of your data. Okay, so again, process your data quickly, because if you wait for next week, I'm sure that you will never process them. Most of the time this is the case, and then do that very quickly. And again, with the recent software and all the tools we have today, the idea is really to do the processing just right after the observation itself. And this is very important. When you are close to your observation, you know exactly what you have done. You know why you have different set of flats or darks or things like that. So you have that in mind, and it's much easier to do it. Okay. By the way, this is, I told you before that I recommend you to start by using your spectroscope on a bench, on a table. And this is the same idea. When you have done that, process your data on the bench and make really before going to the telescope, because if you do that, you will control, you will understand the data reduction process, you will understand what the images must do in this process, and then you will know exactly what you have to do during the acquisition session. Okay. I hope I'm not speaking too fast. Anyway, we'll have the discussion afterward. I've almost finished. I just want to go to this important question. What is a good observation? What makes a good observation? For me, this is very simple. The difference between a good and a poor observation during one night is, in fact, you have to understand that you have to take some time to install your instrument, to tune your instruments, and to make sure that the spectroscope matches the telescopes and so on, and everything is well balanced and is quite homogeneous. But when you start observing during the night, you cannot change the telescope diameter or the telescope focal length or the spectroscope resolution or whatever. So everything is fixed, and during the night, your only mission is to put as much light as possible into the slit. Okay, so this is really the idea is that the more photons you put in the slit, the better the quality of the observation. That's it. That is simple like that. So your mission during the night is to put as much photons as possible in the slit. To do that, you have to make sure that the star focusing is optimal. Okay, and you have to make sure that the guiding is also good. So by guiding, I mean that the target, you ask the mount to put exactly the star in the middle of the slit and not 3 pixels above or below, because the slit itself is few pixels wide. Okay, so it's very precise. And the other point is that make sure that the auto guiding is correct, because if the auto guiding, if you don't have the right parameters, probably the mounts will oscillate around the slit, and each time that the star is beside the slit, there is no light that goes into the spectroscope, and this is sometimes which is lost. Okay, so if you do that, if you put as much light as possible into the slit, whatever is the size of your instrument, it means that you will improve the signal to noise ratio of your result. Okay, so the spectrum will be less noisy if you have a good high quantity of light going into the slit. It will be less noisy, and this is really the main quality of your observation. You can see that in another way. You can consider that if you do that, you will reduce the exposure time. I told you at the beginning, if your instrument is not properly set up or tuned at the beginning, if you observe Vega, maybe it will take 5 seconds, where normally it should take 0.1 seconds. So if it's only 5 seconds, we don't care, it's not a long time. But of course, if you go to a fainter star, if you have to observe it during 10 hours or 10 minutes would be enough, this is a very, very big difference. Okay, and if you do that, you will make, of course, more observations during the night, and also so at the beginning, you will not make a lot of observations, but when you start being productive and when you want to collect as much data as possible, it becomes important to know how many observations I can do during the night. And if your setup is not tuned, you will lose time and you will lose observations. So you have some observations, some phenomena in the sky that are moving fast in few minutes. For instance, if you take the Lyrae stars, they are at some moment at the maximum, at the Blaschko maximum, they change in few minutes time range, and in this case you are very limited by the time of the observation. So in this case, also you have to have the best conditions to have a better SNR. And again, another way to see this problem is that you may save money, because another way to compensate a bad tuning of your instrument is just to have a bigger telescope to collect more lights, and then you will also, by increasing the telescope diameter, of course, you will reduce the exposure time, but it's much more efficient and it's less expensive to do that by tuning the instrument properly. Okay. Well, I still have, I think, really few slides. I want to talk to you about this Solex project. So this slide, I've already shown it during the last webinar I did present some months ago about the Solex project. So the Solex project, this is a project which is proposed by Christian Brill. And well, within Shelyak, we propose a kit of all the optical elements, and this instrument is made by 3D printing. So you make your own instruments with the available STL files on the Solex website, and we at Shelyak, we propose a kit of the optical elements to make a Solex, and even a StarX. So the Solex is a solar explorer. It is made mainly to take images of the sun. And StarX is the usage of the same instrument on the stars. Okay, so we just add a guiding unit to make sure that we can see the star we want to observe. But this is exactly the same instrument. And the idea is really to have something very basic, very easy, that you make yourself, so you perfectly understand how it works. It is easy to build and to tune and so on. And it's a wonderful instrument. So to take a solar image, in fact, we scan the sun, and you can even have, well, we need a small instrument. A small instrument is enough. And you can just stop the mount and let the sun moving across the slit for a few seconds, 2.5, well, in this case, 2.5 minutes, roughly. And the idea is that you take a spectrum at any wavelength you want, because you can rotate the grating. And then after that, we rebuild the image that we extract in a given wavelength. Well, we scan the sun, so we take columns by columns, and we use the software to rebuild the images that we have behind here. So this is a spectrohelioscope. So the idea is to take an image at a very thin wavelength, so we can even see the Doppler effect. If you look at some detail, it's just incredible, and you can take images at any wavelength you want. So it's really a small, fun instrument, and you make it yourself, and of course it is affordable. So I've put the website here if you're interested. Really, I think that for the AAVSO, it is something that is incredibly interesting to start in spectroscopy. Okay, and at the beginning we start by taking sun images, and afterwards we can switch to these stars. Okay. Well, by the way, I've built my own Solex, and we have this small instrument, and again my old mount, and so the Solex is here. We do protect it with aluminum paper to make sure that there is no so this is to protect from some light leakage, and to protect it also from the the heat of the sun. So I was lucky because I had some great opportunity to observe in wonderful conditions. It was in last May, and here is my own pictures that I took with the Solex using the INTI software, which is a software in which you just have to put your file that you taken during your observation, and all the processing is done totally automatically. So really, the image I show you here is what goes out from the INTI software. With absolutely, I just have to select the file and to click on one button, run, and that's it. That is the result. It's incredible. Okay, I've finished. Lauren, you did talked about it, but I've written a book some time ago in which you can have a lot of information on how to start in spectroscopy, and of course a lot of things that I told you today are in this book. Okay, I think I'm done. So now here is our job. This is a picture that I like. This is in the Milky Way, of course, close to the well, I don't remember exactly. This is the Cygnus, one star Cygnus. Each of these stars is interesting to look at. So you know that if you are doing imaging in a single image, you have many stars. Now let's work all together to take each single star in this image and extract the spectrum from this image. It gives you an idea of the huge and wonderful task that we have in front of us. Okay. Thank you very much. Thank you for your attention. And of course, I would be happy to have some questions and discussions.
Thank you very much, Francois. That was excellent. Can you hear me okay?
Yes, perfect. Yep.
Okay, great. And okay, good. My video still works. So I did have a minor technical issue about halfway through your presentation. So there were a couple questions that I think may not have come through. If we get to the end of the Q&A and one of your questions was simply not addressed, please just go ahead and submit it again. So let's start out with a question that was there before the Q&A box got cleared for me, which was, is a star analyzer grading sufficient for recording the redshift of quasars, or would a different instrument be needed for the job?
Well, it's my first reaction would be maybe not, but I know I'm very prudent because, well, maybe Lauren, you would be able to reply to this question better than I do, because I'm always surprised by what we can do with the star analyzer. And what I can tell you is that a star analyzer is not a slit spectroscope. So really what I talked about today is mainly about slit spectroscope. And if you use a star analyzer, for instance, you cannot use a calibration light to do the calibration. Well, for technical reasons, I could explain how to do it. So you may have some difficulties to have a very precise wavelength calibration, and when you want to measure redshift, in fact, of quasars or anything else, you need two things. You need to have a very good calibration, and also, well, depending on the object, you have to have a very good resolution. So the case of the quasar is a little bit different because the quasar has a very high redshift, so it's obvious, and you don't need a high resolution. So well, I cannot tell you. Probably yes. I think the 3C 3373 quasar, the most well-known one, has been observed with the star analyzer. Do you know it? Maybe you did it, Lauren.
I have not done it myself yet because I can't do it with a non-tracking telescope, but I have seen several examples of amateurs measuring quasar redshifts using tracking telescopes. It seems like for the brightest, like you mentioned, 3C273, Biela Certe is another. For those, it's fairly easy because, as you said, the redshifts involved are so high. As long as you can get enough exposure time, probably 20 minutes or more of exposure time at a low dispersion, then yes, it is quite possible. You mentioned that you can't use a calibration lamp. That's correct, and that makes it tricky to measure redshift when you don't have a zero order star as reference in the frame. Generally, at star analyzer resolutions, you can build a reusable calibration for given equipment setup by shooting a star that's like Vega or something where you can easily measure the central line wavelengths. And then the resolution of the star analyzer is so low to begin with, you can assume that you're not seeing any radial velocity effects. And then you can use the zero order star image next to the spectrum as your calibration point. So you probably knew that, but I'm saying that for the other people here.
Yeah.
You can use that technique to measure quasar redshifts.
And I like the way you said you have not measured it yet.
Not yet. Hopefully soon.
Yeah.
All
okay.
Right. So next question comes from Patrick Kavanaugh, who asked, is it okay to spend some nights doing spectroscopy and other nights astrophotography or photometry? Presumably, is it easy enough to switch between the two?
Yeah, yes, well, yeah, it all depends on your equipment. Well, for sure, this is very useful, in fact, to have imaging and to do photometry in parallel to spectroscopy, because if you do photometry, you have the overall magnitude of the object you want to observe, and if you are doing spectroscopy in parallel, then you can see how this energy is spread out along the wavelengths. Anyway, maybe your question is more technical regarding, so can I switch from one instrument to the other? I would say if you remove the spectroscope from the telescope and replace it by your acquisition camera, your photometry or imaging camera, that's not a big deal, but you have to rebalance, you have to manage the cables and so on. So I know that there is a lot of people who have a dedicated instrument for spectroscopy and a dedicated for photometry or imaging. And you also have people with bigger instruments that have multi-port system on which they can put several instruments, and then they have one spectro in a port, one camera in another port, and so on. So you may have anything from any configuration. But of course you can say one day I observe in spectro and the day after in photometry, and this is again scientifically useful.
Thank you. To add on to that, I believe that I've heard of amateurs doing spectrophotometry using piggybacked telescopes, like a smaller piggyback telescope to do the photometry. Have you heard of that? Am I misremembering?
Yeah, but well, in this case, the advantage is that you really can do the same at the same time. The two, you can do both spectroscopy and photometry at the same time, and this is useful. Yes. Okay. Now, maybe I don't know what is exactly the question from Patrick. If we are talking about observing the same target in photometry and spectroscopy, or it is just to switch from one instrument to the other.
Mm-hmm. Yes, I believe Patrick's was about switching, but I was just curious about if amateurs do actually do that piggybacking photometry in practice. So, all right. So the next couple of questions that we have here are about guiding. So Nathan Crum had asked, what is the best way to auto guide when the star is being split apart by the slit?
This is a good question. In fact, of course, when you have the star and across the slit, in fact, the star almost disappears in the slit. But in practice, we always have some light. So we have the wings of the star that are still visible around the slit. And I know that the few years ago, there were some system for the auto-guiding, we have specific algorithms that were able to manage the star split by the slit. As far as I know, today, I think that nobody cares about that. You just use the auto-guiding software as it is, even for a normal star, and it works perfectly. So, and you don't have to care about the fact that this is not a problem, in fact, for the auto-guiding process if the star is split by the slit.
Interesting,
Okay.
thank you.
I would say that, in fact, the fact that the star is split by the slit increases the sensitivity for an misalignment of the star. So it even improves the system.
Very interesting, thank you. So the next question about guiding comes from Patrick Kavanaugh, who had said that for bright objects, he assumes that a guide scope is not necessary, and he'd like to know, where is the borderline between using and not using guiding programs like PhD?
Where is the... Whoa, well, there are two things. There is one thing which is so of course the plate solving today, it's very useful to make sure that you are pointing at the right star, and it works perfectly. And it generally speaking, it helps to control your mount. And with this plate solving in the guiding image, you can do a T-point model to have a very precise pointing of the mount and so on. So it's really a wonderful tool, and I know I'm very impressed by the plate solving, how it helps to point at a star. And with this system, it becomes very difficult to observe the wrong star. In fact, it's very efficient. Now, having a plate solving system to point at the right star doesn't mean that you don't need to use a guiding software like PhD, for instance. It's always important to have a guiding system. Again, it depends. If you have a very good mount, and if you have a wonderful T-point model for the mount control, and if you have short observations, say 30 seconds, 1 minute, maybe you better have not to use the guiding, the auto guiding, because in this case, the mount will have a very smooth movement, where the auto guiding may have give some oscillations in the guiding. So it may help, but generally speaking, you still have to have the auto guiding ready and properly tuned. Okay.
Right.
This is something that really changes nowadays, because we can access to a wonderful mount and wonderful tools. So this is changing a little bit.
Okay, thank you. The next question comes from Jason Adamick on Facebook, who had asked, is being very accurately polar aligned essential for spectroscopy?
So again, what is important? What is important at the end is that you put as many photons as possible in the slit. So you can, in some ways, a poor mount alignment can be compensated by a good tracking and auto guiding system. Okay, and even depending on in some situation, when you have, it happens that you have some gap in your mount in the delta axis of your mount, and then the guiding will make some random movement vertically. In this case, it could be better to have a small misalignment of the mount and use the auto guiding to compensate for that, because if you do that, the mount will always compensate in the same direction, and then you will avoid having a large movement of the mount. But again, I know I did have this problem with my old mount, the one that I showed you in my slides. But today with the mount I have a 10 micron mount, which is just wonderful, and I have absolutely no gap. And in this case, the problem doesn't exist. Again, sorry, can you tell me again what was the question?
The question was about whether a very accurate polar alignment is essential for spectroscopy.
Yeah, so again, dipolar alignment depends on if you have an observation that lasts for 2 hours, you have to make sure that during these 2 hours you put the star in the slit. And in this case, depending on your setup, and again, I come to this sentence, always know why you are doing what you are doing. It's important. What will you do to make sure that you have this control of the star inside the slit? I've seen a lot of cases where the auto-guiding is more efficient than a perfect polar alignment. But this is always the same. A good polar alignment will always help to have good tracking.
That makes sense. Thank you. Okay, so the next couple of questions have to do with various kinds of calibration. First of all, Michael Napper had asked, when you are taking spectroscopic images, why do you need to take darks, flats, and etc.?
This is a good question. This is an important question. I would say that for dark, flat, and bias images, it is almost for the same reason than for imaging. Okay, you have to understand that. I take the example of the bias, for instance. We are looking for what energy is coming from this star at given wavelengths. And we'd like to measure this energy relatively to the other wavelengths. And to do that, we have to make sure to know exactly what is the intensity of the light coming from the star. And the problem is that if you take an image with your CCD or your CMOS camera, the intensity of the light of a given pixel will not be only dependent of the intensity of the light source, because you have an offset in the camera design. That the offset is made to make sure that all the measures of the light are always positive, and there is no risk to have negative values, because the converter, the analog to digital converter inside the camera cannot manage negative values. So to avoid that, we put an offset in the camera, and then it means that if we have, I would say, 100 ADUs, so counts from the star, we add some of the ADUs for technical reasons. But what is interesting is just to have the real value coming from the star, and we have to remove it, to remove the effect coming from the instrument itself. So this is I take one example. You have other reasons to do it, but you need to take bias, dark frames, flat and calibration images, generally speaking, to make sure that you will be able to process properly your data afterwards. I hope I'm clear enough.
I think so. Thank you. Okay, and our other question about calibration. Okay, so Tatsuji Tanaka had asked, how can I calibrate out the light pollution in a city? I mean, will I need another data set of an area with no stars in it? How would I do that?
It's a good question. Well, it depends if you want to measure the light pollution in your city, or if you want to compensate your observation from the light pollution. Of course, if you want to measure the pollution, the light pollution, you have to have a reference, a perfect reference. But again, using if you are using the flat dark frames and so on, you will be able to measure what comes from the sky really, and you just have to not point at a star and just point at the sky itself, and you will measure the light coming from the sky. Now, if you want to compensate your observation, star observation, from the light pollution, skylight pollution, it's quite easy if you have a slit spectroscope. Again, this is not something that you can do with a slitless spectroscope like the star analyzer, but if you have a slit spectroscope like the LP, the UX, or things like that, because we have a slit, and in fact, this is all the light going through the slit that is spread out and that is transformed in a spectrum profile. And if you do that, we just put the star at a single position in the slit, which means that all the remaining parts of the slit have the light coming from the sky. And then when you take a spectrum in city center, you will have in the middle of the image, generally speaking, the star spectrum, but above and below the star spectrum, you'll have the sky pollution spectrum. And then during the processing, we will measure the sky pollution on top or above and below the star spectrum to compensate the result from the system. So this is a very important point that really makes possible to do spectroscopy and to do science in spectroscopy and to compensate for some problems in the city observations and to do a great observation. Okay, you can do spectroscopy in city center.
Thank you.
And of course, if you are lucky enough to be in a great country, it's much better to do that a better sky is always better, of course. But,
okay, thank you. And the next question comes from Hamish Barker, who had asked, is the color temperature of the flat lamp critical?
It becomes very technical. Yes, and no, it depends on the algorithm that you use behind. We would love to have the ideal flat lamp doesn't exist. Or maybe I should say, like you did, Lauren, doesn't exist yet. Because an ideal flat lamp would be a very, very high temperature lamp, like the stars, to have a lot of energy in the blue part of the spectrum. And the problem is that when you are using a halogen lamp or xenon lamps or things like that, the temperature is quite high, but not as high as stars. So we don't have enough light in the blue part of the spectrum. And the other parameter would be, we would love to have something which has exactly a black body behavior. So if we would have that, if we would be able to have such a perfect lamp, we could say, okay, so this is a black body profile. Then we have the theoretical profile of this lamp. And then we can, just by measuring the flat, we have an absolute value. Okay, in fact, this is not the case. This is not exactly a black body profile, and we don't have enough energy in the blue. So as a result, what we do at the end is that we always take a reference spectrum from a given known star, and known star means a star for which we have a very reference spectrum that we can compare from, and then we use that to calculate the instrumental response. Of course, if the flat is how can I say that, the better is the flat lamp, the less we have to compensate with observing another star. Okay, you have to understand that we are nothing is perfect. So we are trying to do perfect observations with an instrument which is not perfect. And what makes the difference is really the methodology. So we take what we have, we take not perfect lamp, we take not perfect instruments, and because we are clever enough, we can use the computer, we can use some algorithm and so on to improve things and be as close as possible as the truth, in fact, coming from the star. But it's always a question of trade-off and compromise, and we are doing perfections with the imperfect device and elements.
I like that way to put it. Thank you. All right. So one comment that just came in from Timothy Weaver, I'm going to read it out while it's relevant, is if you're looking for a light source that is as hot as a star, maybe a plasma torch is what you're looking for.
As far as I know, so I know that there are systems. So well, this is I keep the door open in case of we have very good news. I think that the plasma torch has has a lot of lines, if I'm right. This is absolutely not a continuous profile, so it's not an ideal system for a flat lamp. Maybe I'm wrong. Again, I know that there are some system. Maybe there are some systems, but for me, plasma lamp means that you have emission lines, and then this is absolutely not something that we can use as a lamp. This is the same, for instance, we could use the sky. We could say, well, the sky has, this is the light coming from the star, so it is at the source, it has a very high temperature. Yes, but the problem is that it is absolutely not a Planck profile lamp and light source, so we cannot use it as a flat.
Yeah,
it's a
that
pity.
makes sense.
Which is also a difference with the imaging, because for imaging we can use the sky as a flat source.
Yeah, I think you're correct about plasma torches having a lot of emission lines. I've looked at a small one through a diffraction grating before, and it's a very beautiful spectrum to look at because of all those little emission lines, but it wouldn't work well for a flat. All right, let's see. So one more question on this topic comes from Pradeep Karmakar, who had asked, is it always compulsory to do the instrumental correction, or can we sometimes just stop after the wavelength calibration?
I love this question. Thank you, Pradeep. This is a very good and important question. I would say two things. The first one is it all depends on what you are looking for. Okay, so again, you have to know why you are doing what you are doing. So if you don't have to do the calibration or to do the instrumental response correction because you have been told that you have to do it. It's not an enough reason. Okay, so it really depends. And I like this example. A wonderful program, for instance, is to observe as many B star as possible to detect new BE star. BE star is a B star in which you have some emission lines. Okay, and these emission lines are, in some stars they are permanent, but in a lot of stars they are varying over the time, and we know that we still have a lot of BE stars to discover. So to do that, in this case, you just have to observe a lot of B stars and look at the H alpha line and look if the H alpha line is in absorption or in emission. And if you have this kind of observation, you don't care about the calibration, even the wavelength calibration. So it's not precise. We know in the system why is the H alpha. We can recognize it very easily because B stars are hot star with a smooth profile with a few H hydrogen lines. So it's obvious to see. So you can just use the raw image and you don't need to process anything. Okay, so in this case, it's enough. So it's important. So you do the calibration if you need it, okay, and don't do it if you don't need it. Also, you have to remember that in a spectrum, we have roughly two kinds of information. The first is along the x-axis, which is the wavelengths, and the other one is along the y-axis, which is the intensity, the relative intensity of the profile. Depending on what you are doing, for instance, if you are measuring the relative density of this gas versus this other gas, the question is more related to the Y value of it. You have to look at the intensities. Now, if you are looking for exoplanets, in this case, the key is the Doppler effect, and the Doppler effect is linked to the wavelength calibration. So depending on what you are doing, you are more looking at the x-axis or at the y-axis of your spectrum. Okay, so really keep in mind that it depends on what you are doing. Now, there is another reply to this question, which is when we are doing spectroscopy as an amateur community, together with the professional community to have new observations, it's important to say that, okay, when I do an observation, I probably have a good reason to do that because we are doing a survey of this kind of stars, B stars, for instance, for the BESS program. And so we have good reasons to do it. But the most important is that we keep this observation in memory. We put that in a database that can be used by anything else. but anybody in the world. And it may happen that this observation will be useful in 10 years from now because there is a star that is exploding somewhere, or I don't know, we need a reference to measure the period of a variable star or something like that. And in this case, it's important to say that, okay, so when I do my observation, I do it for my own need, and I know why I'm doing this observation. But on top of that, I will put it in a generic format and make it, I will do my best to make the best possible corrections to have a good observation that can be used by anybody, and we don't know why it will be used for. Okay, so and in this case, it is better to have a data reduction process which is clean, to make sure that we have a good correction of the instrumental effects, a good wavelength calibration, and so on. Okay, to have something as pure as possible to be used by anybody. You know, if you look at this is something which that was very surprising to me when I started in spectroscopy. So we looked at some professional data, so very high level data, and in some of them we have seen some the poor, it was a pity, so it was bad measurements, and they say, hey, professionals are not good. And in fact, if you look at the reason for that, it was done for a given purpose, for a given goal that was absolutely not, for instance, the wavelength calibration. So they didn't care. And so we say, well, there are bad measures. No, they are not bad measures. There are measures that was made for a given goal, which is not mine today.
Good enough for its purposes. Yes. Yep. And I would like to add on to that the AAVSO spectroscopy database, AVSpec, will accept non-instrument response corrected spectra as well as instrument response corrected spectra. You're correct, Francois, in saying that it's, you know, you should aspire to instrument response correcting your spectra so that they are most useful for people in the future. But we do encourage you, you know, even if you forgot to take a reference star spectrum or something like that, we do encourage you to submit your spectra anyway.
And also something that I can add here is that, in fact, the correcting correcting or not the instrumental response response, for instance, sorry, this is something that belongs to the data reduction process. And in fact, you have to understand that when you become a little bit rigorous, the data reduction process is linked to the instrument more than to the observation. Okay, so if you have an instrument, you should always process the data the same way, and then the intrinsic quality of the calibration, data response correction, and so on is always the same. It depends on your instrument, and the data reduction process belongs to the instrument. Okay, so whatever is the observation you do, you'll always use exactly the same process. It will be easier for you. It will be more repeatable. And then in this case, it's better to include this response correction. I hope I'm clear enough.
Thank you. I think that was quite clear. So our next few questions that we're going to take are on the topic of equipment. So first of all, we have a question from Conrad Cardano, who has asked, is there any company that is working on an objective grading spectroscope for a telescope?
Well, I don't have I don't have a clear answer. I know that we don't have such a device. Well, the only grading we have is the star analyzer. I know that some people put the star analyzer in front of the lens of DSLR, for instance, and it works. But this is what we call the objective grading. But I know that the problem with star analyzer, for instance, is that we are very limited by the maximum diameter of the system. And of course, if you want to put a grating in front of the telescope, it will have a huge diameter, and the price is huge, and you have to have something really keeping the same density of lines all along the whole diameter, and then this is something I've never seen it. In fact, I don't know. I know that we have some prisms, objective prisms, but well, I don't have a lot of experience in that.
Yeah, I have not seen anything like that either. All right, next question from Michael Nuss. What real-world results or differences are there between a purely reflective system, such as an RC, versus one that incorporates lenses, such as a Schmidt-Cassegrain?
Also, this is a good question, and if you have a purely mirror instrument, the direct effect is that it is achromatic. Achromatic means there is no chromatism, and the chromatism is the effect that makes that if you take a lens, for instance, if you take all the red rays, they will not focus exactly at the same plane, at the same focal plane as the blue rays. Okay, and then depending on the wavelengths, you will not have exactly the same focal plane. And so this is what we call the chromatism. And of course, the result is if you want to observe from far blue to far red with glass, it is very complex. Okay, it is very difficult, and especially when you do optics, the problems appear mainly in the blue part of the spectrum. Okay, if you can see it we have seen some very old optics and for which the blue part was was poor, in fact was bad. And the result is that if you take the spectrum, this is not a thin line, but when you arrive in the blue part, it becomes wider, and this is what we call the fishtail effect, because the spectrum becomes wider in the blue part. So it's not necessarily a big deal, but you will lose some resolution for sure. You will lose some light for sure. So you can imagine that if the spot in the red part is very well focused on the slit, so all the red energy will go in the slit. But if the blue is bigger, then only a few percentage of the blue rays will go into the spectroscope. So we lose some sensitivity, and you will lose also some resolution. So it's better to have something achromatic. Now, if you are observing in high resolution in blue or red, it's not a big deal. You just have to refocus or to focus differently if you have this kind of instrument. So to make it short, nowadays we like to go more and more towards the blue and the infrared, and this is really one of the main reasons for which we have developed the AAVSO instrument, which is a purely mirror instrument also. So we use cylindrical, spherical mirrors for the collimator and for objectives inside the system. So the instrument, the spectroscope itself is purely achromatic. And if you use this with the purely achromatic telescope, like a Ritchey-Chrétien, for instance, which is made only of 2 mirrors, there is no glass, then you have a perfectly achromatic instrument. And this allows us to go very far in the blue and very far in the red. Okay.
All right. Thank you. Next question from Subhash Gadam. What is the typical width of the slit in a spectrograph?
Well, in our instrument, in most of our instruments, the typical slit is something like 25 microns. Okay, so the idea is to have a slit which has the same width of the star image at the focal plane of a telescope. And so the star image size depends on 2 parameters. The first is the seeing of your observing site. So if you have a good seeing, you may have well, less than 1 arc second of seeing, and in a more usual sky you will have something like 3 arc seconds. So this is due to the turbulence of the sky. Then the star image is not as sharp as possible. And the other parameter is the focal length of the telescope. So if you have, generally speaking, if you have a bigger telescope, you have a bigger focal length. well, even of course, if it depends on the f ratio, the key is really the focal length. But the bigger the telescope, the wider the slit image. This is the reason for which it's something absolutely key in spectroscopy, which is if you have a bigger telescope, you will have to have a wider slit to catch all the light from the telescope. Okay, and this is not negotiable. Sorry, this is for optics and optical constraints. And if you open the slit to catch more light, and if you want to keep the same resolution, you will have to have a bigger spectroscope. Okay, so this is really if the telescope is bigger for a given resolution, the spectroscope will be bigger for this reason. And this is why we are lucky as amateurs, is that we are working with small telescope, which means that we can use small spectroscope to have the same resolution.
Instead of those spectrographs that take up entire rooms at major observatories.
Absolutely, absolutely.
All right, so we've got actually two questions related to that. So first, let's go to Bobby Napier's question. Does the focal ratio make a difference in the instrumental effects? So like, what's the difference between an F10 Schmidt-Cassegrain or an F6 scope in terms of spectroscopy?
Again, there are wonderful questions. So we can continue for hours and hours. Your questions are wonderful. Thank you very much.
We have a little bit more than 10 minutes left. So.
Okay, thank you. This is of course well, in few words, I'll try to make things simple. If you have a fast telescope, say a Newton telescope at f5, f3, f5, f4, f3, well, f3 is really the maximum. Of course, for a given diameter, you will have a shorter focal length. If you have a shorter focal length, you will have a smaller image, star image size at the focal plane, and then you can close the slit and then increase the resolution, or put more slit in more light in the slit. Okay, so this is really really the key. So for a given diameter, it's always better to have a fast aperture, low f ratio. But the problem, if you do that, if you have a beam like that, in front with a f3 telescope, for instance, it means that the optics of the spectroscope behind must be able to take all these images. So it must also have the same f ratio. And having a high f ratio for an instrument is always, optically speaking, it is always complex. This is the reason for which in photo, if you take a photo lens, if you have for the same focal length of a photo lens, if you have an f2.8 lens, it will be much more expensive than the same wavelength, same focal length at f4 or f6. Okay, so this is really because you need, it is more complex to manage a very open beam, a fast beam, and it must be optically compensated by a more complex optic. So it's always a question of trade-off. Okay, it's really well, it's a trade-off. So for sure, in optics, if you want to go below f3, it becomes really challenging. Okay.
Mm-hmm. That makes sense. Thank you. Okay. So Hamish Barker has asked on that topic, if a spectroscope needs a slower focal ratio than is available from your telescope, can you use a Barlow, or will that introduce too many chromatic effects?
Of course, it's a good question. If you have, well, if you well, it's always better to have the right f ratio, the same f ratio for the telescope and for the spectroscope. This is the best way to have the optimal total efficiency. And so it's important to look at the f ratio of your spectroscope and make sure to match with the telescope. And of course, if you don't have exactly the right f ratio, you can change it either by reducing the focal length with a focal reducer, or increasing the focal length with a Barlow lens. Okay. in every case, you will add some glass. That's right. And it really depends on how you will use it. So it's a question of trade-off. Well, for sure, for me, if you are starting in spectroscopy, don't take care of everything, just make your first spectrum, and it will be time afterwards to look at these details. These are not details. This is very important to have an efficient instrument. But if you at the beginning, if you don't have the right F ratio, this is not a problem. Your observation will work. You will have a spectrum and you will be able to work with it. So it will not be optimal in signal to noise ratio. Maybe you will not take the benefits of your telescope or your spectroscope, but anyway, on a bright target, you will always have a spectrum. So this is very important for beginners. Okay, so don't spend too much time to start in spectroscopy. Observe with what you have. Now, if you want to change your F ratio and your focal length with a Barlow lens or a focal reducer, this is a trade-off. So will I get some advantage? What I will win and what I will lose by adding this device? So if you have, for instance, an F10 telescope, Schmidt-Cassegrain telescope, usually at F10, and you have a spectroscope which is F5, F6, you better have to put a focal reducer because the difference is too big. Now, if you have a telescope which is at F8 and you have a spectroscope which is at, I would say, F8.5, personally, I think don't put anything because the gain, the performance increasing will be so small that you will lose it by adding some glass in the path. And by the way, think that if you have a Ritchie-Christian telescope, purely mirror, and a UVX telescope, for instance, purely mirror, so you have a fully achromatic system. In this case, it's really a pity to put some glass in the middle because you will introduce high achromatism. Well, yeah. High, depends on what you are looking at.
Yeah. Okay, thank you. So speaking of achromatism, we had a question from Bernhard Schultz, who has asked, how do you deal with atmospheric refraction?
That's also a very good question. So the atmospheric refraction means that the star is not a pure point, but it's a small spectrum, vertical spectrum, because of the diffraction of the refraction of the atmosphere. And well, I would say that the first way to deal with that is to not observe too low at the horizon. And of course, it's better to observe above 30 degrees to make sure that the atmospheric refraction is almost negligible. Now, of course, if you have an event, if you have a nova that explodes tomorrow, it may be at the horizon, and maybe you don't have the choice and you cannot wait, and well, it happens, of course. So in this case, so either you increase the slits width and you lose some resolution, but to make sure that you will catch all the light, or there is another solution, which is to rotate the whole spectrum, the spectroscope around the telescope versus the telescope, to put the slit vertical. Okay, and in this vertical compared to the Earth, and in this case, the small spectrum that makes the star will be included into the slit vertically. I don't know if I'm clear, but this is really the idea.
That is clear. Yeah, thanks. Good advice. Okay. And we have another question here related to the slit. Michael Nuss had asked, so specifically for a fairly low resolution slit spectrograph like an LP or LISA, if you want to shoot something non-stellar like a comet with a long focal length scope, he's giving an example of 2,100 millimeter focal length. What should you do about the slit size? Setting the slit size.
In fact, in this case, for me, for sure, this is the standard slit, which is the 23 or 25 microns. For a simple reason, with this focal length, I know that the size, the size of the star image, it is typically RC8 or 8-inch Schmidt-Cassegrain telescope. For this focal length, you will have roughly 20-25 microns FWH, so width of the star image in the focal plane. And this is also the optimal slit size for the LPA or the LISA resolution. So for such a small telescope, we are very lucky because this is the good value for both the telescope and the spectroscope. The problem appears if you take a bigger telescope. If you have a 400 millimeter telescope, for instance, then the star image will be bigger. So depending on what you are looking for. So if you want to have the resolution, you keep the nominal slit of 25 microns, but you know that you will lose some light. You'll have the full resolution of the instrument, but you will lose some light. If you want now to get some faint target and to go for very faint object, you may open the slit. And if you may open the slit, if you open the slit, you will lose some resolution. But you can, for a bigger telescope, you can really choose between the resolution or the brightness. Okay, in some way. But at 200 millimeters diameter, which is 2 meter focal length, this is almost the same. And then if you increase, in fact, if you increase the slit, you will not increase the detection of the system, and you will lose some resolution. So it's a pity.
Okay, thank you. So looks like we've got 4 more questions. I think we're going to need to speed up a little bit to get through all of them before we have to close things down. First of all, Michael Nuss has asked which objects or phenomena would be best as targets to observe at a medium resolution, so somewhere around R1000 to 5000.
Oh, your life will not be enough, and so you have many things. Well, it's difficult for me to reply to this question because you have thousands and thousands of objects that we can observe with our instruments. And of course, if we go lower in resolution, so the resolution of 1000, resolution power of 1000 is something really a medium resolution, you can access so many objects. So you can object a lot of stars, a lot of nebulae, a lot of planetary nebulae, a lot of well, really there is no limit. There is absolutely no limit. So well, I cannot, I don't know what I can answer to this question. So really, you will see that when you do spectroscopy, you even in spectroscopy, well, spectroscopy is somewhere, it is a niche in the astronomy, but you have to be specialized in one area because you cannot observe everything in spectroscopy. I have shown you the picture of a star field in the skies. There are so many objects, so there is no limit, and you will see if you want to observe. Personally, I'm a mechanician. And I like the Doppler effect because I understand it perfectly because this is basics. This is not quantum mechanics and so on. And to do that, I prefer to work with a high resolution, but it depends on what you are looking for, what is interesting. So do you want to observe for years and years the same type of object, or do you want to just jump of any event that arrives in the sky? There are so many things to do that there is really no limit. I'm sorry, I'm not sure that this is a good answer, but this is so open question.
I think it is a good answer. It's really, you can observe just about anything. The AAVSO actually has a list, which I'm going to go ahead and paste into the chat, it's on the spectroscopy observing section page, and it just has some suggested types of targets with suggested resolutions for observing them and making various kinds of measurements. So I'm going to put that in the chat while you are answering the next question, which is from Patrick Kavanaugh. And Patrick asked, when would be a good time to migrate from low resolution spectroscopy using slitless diffraction gratings, such as a star analyzer, to slit spectroscopy with a fancy spectrograph?
Wow. Again, this is a very open question. I know that well, the star analyzer and low resolution diffraction gratings is a wonderful system to jump into spectroscopy. This is cheap. This is close to the setup that you usually use for imaging and photometry. So there is a lot of advantages. Now, switching to slit spectroscopy means that you can there are a lot of advantages. So you can use some calibration light, because you will the calibration light is an extended object, and in fact with a slitless spectroscope you cannot observe an extended object. You are limited to stars because the extended object will make an extended spectrum, and which is totally confused, and then you don't have you cannot use the spectrum. So you can use calibration, you can use you can observe extended object, you can correct from the sky pollution, because as I explained, at the same time as the star spectrum you will observe the sky background spectrum, so you can correct it from your observation. And there are a few other good reasons to switch to slit spectroscopy. But the star analyzer or small devices like this still have advantage. I know, for instance, Robin Leadbeater in UK, he's using the star analyzer, and he loves to observe novae with this kind of system, because the advantage is that it's very simple. You are not losing a lot of light, so you can observe very faint object with a star analyzer. Okay, so it really depends. Now I can tell you that I would say that 95% of the observations in spectroscopy or even more, 98% are made with slit spectroscopes.
Okay, thank you. And this is our last question for now. Comes from Patrick Kavanaugh again, who has asked, in your experience, what is the background of most of the people in amateur spectroscopy? Engineers, scientists, teachers, liberal arts majors? What have you observed?
Well, I know in my book I start with with that. When I see people doing spectroscopy, I like to say that in fact there are people coming from the science itself. So they want to understand they've read books about physics and astrophysics, and they want to understand how to how the universe works. And so these are part of people are coming from science, and then there are most of them there are scientists, there are engineers, or things like that. Beside that, you have people who love to make their own instruments, to do it yourself, to polish the mirror, to do some computing, some software development, or to make their mount, and so on. And then for that, a spectroscope is just a wonderful instrument, because it's a fun part of a piece of optics, and this is something very great. And so we have a part of people doing spectroscopy that come from this area. And the third area is people coming from the observations. They like to use their telescope on the sky and to make real observations. And I know a lot of people saying, well, okay, I've made great images, I've made wonderful images. No, I'm tired to do always the same kind of source, and I'd like to do something else. And then the spectroscopy is something wonderful. It is infinite. We will never see the end of this story. And so this is a wonderful new field of game for these guys. So really, I like to say that you have people coming from science, you have people coming from techniques, from the instrument, and you have people coming from the observations. And when doing astronomy, in fact, we need the three of them. And in astrophysics and in science, I like to say that any discovery is made either thanks to a new science scientific discovery, a new model, for instance, or it comes from a new instrument like the fiber or the CCD cameras or adaptive optics or things like that, or it comes from the observers, because you have an event that has been discovered, like a nova in the sky in early August, or somebody who did observe the same star during 20 years, and after that he knows the periods, the many different periods, and so on. So this is the astrophysics is a permanent discussion between these three kind of people. And when we do spectroscopy, wherever we come from, we have to manage a little bit all these fields. We have to be in the field to do observations. We have to understand what kind of science we can do and what means these observations. And we also have to understand how works the instrument. So this is why spectroscopy is so wonderful activity, because it requires to make things. And I promise you that when you do that, you really better understand the challenges of all the most advanced research in the world today, and we better understand, and we can discuss with all the professionals that are working on the trying to understand if there is some life elsewhere, or are there multi-universe or things like that.
Thank you, Francois. That's very well said. Okay, that's it for our Q&A. I'm going to go ahead and start sharing my screen here. All right, there we go. So time for the closing announcements. First and most importantly, I want to give a huge thank you to you, Francois, for sharing your time and knowledge with us today. This was really excellent, and I've seen that we've had a whole flood of thank yous coming in through both our Q&A and chat, because people are really happy after all this wonderful instruction. And also, before I close the webinar, I would like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All Sky Survey project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO.